Well, howdy. Now, this is one of my favorite ones and one of course, the most complicated ones. What it is you have a couple of dumbbells, and we're going to assume that the weights are very thin. So they're large on one side and they're large in radius, but they're thin this way so that we'll be able to ignore their thickness later on when we do moments of inertia. So we have two of them. And they're both rolling towards each other, so that at this point here, since this one's going at some speed v and this one's going at some other speed also v, they're going to hit and then they're going to break apart. So sort of how does that look? It looks sort of like, you know, an eye going this way and then an eye going that way. They hit each other, sort of like that. And then they come off after they hit each other, and you can imagine that after they hit each other, you know, this guy is going to be spinning this way, and this guy here is going to be spinning the other way, right? So he'll be spinning that way. Actually, that's right. So, but they'll still be going away from each other at the same time. So there's lots of stuff going on in this. They hit each other and they come apart, and you know, things happen. And this is kind of interesting because we have all sorts of things going on. We have a collision here where the total momentum is 0. That doesn't really help us very much, except for saying that, you know, if we have the same speeds coming in here and the same masses, I'll be calling these 2m. There, you know, we have the same momenta, so that the total momentum is 0. Well, what's that going to mean? These two objects always have to have equal and opposite linear momenta. So when you come out of this, if this guy has a speed u, the other guy will have a speed u as well, just to keep those momenta equal. Also, we have two angular momenta. You know, as they're coming in, well, actually we've got two different kinds of angular momentum. We've got the angular momentum from these things rolling, and actually I'll call this nu for its angular speed. I'll be using omega for something else. I'll be using omega for what we want to find, which is going to be another angular thing. So this guy's going to come out spinning around this axis, right? So we've got our dumbbell, and when it's just moving along, it's spinning around this axis. So its spin angular momentum, its intrinsic angular momentum, is along this axis here. But it also has another angular momentum from its position, right? So we're going to calculate the angular momentum from the point of impact. So the angular momentum of this guy is going to be the angular momentum at the center there. You could also calculate the angular momentum of each of the weights, because we're going to ignore the weight of the bar, which is going to be this R cross P thing here, right? So it's going to have some sort of R cross P effect there. So the interesting thing about that, this second angular momentum, is that these two guys have exactly the same angular momentum because of the R cross P thing, right? That's also going to be this distance times this momentum, right? Which is whatever that component is, that's half the length here. So that's mvl over 2. And actually this is going to be going around this way, so it's on the right side of this line, so it's actually a counterclockwise direction, so it's a minus sign. It's a negative angular momentum. But if you look at this one over here, this is also on the, if you look at it, it's on the right side of that line. If you're looking along the radial vector, it's on the right side, so it's also negative. So the total angular momentum for this part, the angular momentum associated with the linear motion, strangely enough, is non-zero. Whereas if we were to look at these guys, the weights here, the weight coming this way has its angular momentum along this axis here and in that direction. The angular momentum of the other guy, who's going the other way, right, has the angular momentum coming like that, so it's along the same axis, but in the opposite direction. They have the same mass, they have the same speed, they have the same radius, they're exactly identical dumbbells. So that angular momentum actually cancels, right? So that angular momentum is not something we have to worry about in this problem. All that means is that whatever the angular momentum of the spin is on one side for this guy, it's the same for this guy over here. So just like the speeds. So it's not, or just like the velocities. So that's not, just like the speeds, because the speeds are the same, the velocities are opposite. Same thing with these, the angular momenta are the same, but the directions are opposite. The sense is opposite. So that's going to be the interesting part of this problem, is that we're going to use this to help us find the linear speed over here, because we're going to want to eliminate that, because that's not actually what we care about. We want to find how fast they're spinning afterwards. So we want to find this omega that's going to be how fast they're spinning as they go along the path. So let's see how we'd actually set this up. So all we really have are two identical dumbbells. So if we have two identical dumbbells, let's call them dumbbells. Doesn't work with my dumbbells. My dumbbells are hexagonal. But that's the way things are. Like I said, we're going to have a mass of 2m, so the weight on each side is going to be going to have the mass m, and the dumbbell is going to have a mass 2m altogether. And then there will be a hopefully I remember to cut that out. I was just looking at something. But I think everything's fine. I think everything is fine. We'll find out. Each weight has a radius, r, and the dumbbells have a length, L. And we're going to go with an initial speed of v. Okay. And the drawing I want to do for this is we have our dumbbells physically racing to hit each other along that line so that they hit dead on with these weights, right? So the lower of the left hand and the upper of the right hand weights. And their speeds are v. So we're looking down at this. We're looking in the plane. That's almost all we need to do a find. And like I said, we want to find how fast they're spinning. So we want to find the angular speed, the final angular speed, which will be omega. Okay, so how are we going to do this? Well, this is a collision, but we're not going to use conservation of momentum. We'll use conservation of angular momentum instead. Because like I said, conservation momentum just gives us some of the symmetry properties. Just tells us that, this is a completely symmetric system. What happens to one of these dumbbells is going to happen to the other dumbbell. So that's interesting, but we don't need to worry about it too much. Let's see, then we'll want the equation that goes along with this, which is like L plus L for the initials are equal to m plus m for the finals. These are vectors. Angular momenta are vectors. It's a good idea to remember that. And then we'll, do our thing where we have before and after. So we have v and omega in one direction and v, or v, just v in one direction, v back. And as they come away, then they have u and omega and omega. Excuse me. So that will be sufficient to set us up. All right, then we get to the good part, the part that you've been waiting for. We want to find that omega, and we're going to do it with our plan. So we start with figuring out something that has to do with omega. So we are using conservation laws, and in fact, probably conservation laws are all we need. Well, there's some things we have to do to connect some parts, but other than that, we basically just have conservation laws. And I talked a little bit about this at the beginning. We have 3 conservation laws that we can use. We have conservation of momentum, but all that gave us was that because these are equal, those are equal, right? Basically, we have no momentum, so that's all that's going to give us. We have conservation of angular momentum. We have 2 axes for that. We have the axis where these guys are rolling, but because this guy's rolling sort of this way and this guy's rolling the opposite direction, otherwise they're exactly identical, that in that direction, in that y direction, that's 0 as well. So we have 2 other things. We have the conservation of angular momentum in the z direction, which is down this way, or conservation of energy. So both of these are positive. Both of these have real values, so that's what we're going to use. Both of them have a term with omega in it, right? One of them has an I omega for the angular momentum, and one of them has a 1/2 I omega squared for the kinetic energy associated with that rolling motion. So let's start with the conservation of angular momentum. Let's see what's going on here. So we've got 2 identical dumbbells. So we have 2 identical dumbbells. So they have the same angular momentum, remember, coming in. And this is the linear angular momentum where you've got around this point, around this x, we have that angular momentum. We have, it's L equals R cross P. And that ends up using this L over 2, which is the center of mass of the dumbbell right in the middle of it, times just P is equal to mv. So we have actually P is equal to 2 mv because we have 2 of these weights on either side. So we have 2m because we have 2 weights. We have v, and then we have L over 2. And that's the initial angular momentum in the z direction. In the final, what happens? Well, these guys reverse course and they go in the opposite direction. So we have minus 2 mu this time, L over 2. Plus we have the spinny part going around. That has to be positive because this is negative. Actually, this one's negative and this one's positive, but we'll do it this way. Those also have 2 of those, and those have to be positive. They have to be the same size as the same direction as this because it's conserved, right? So if we've got this positive, this negative, this better be positive so that it can take up the slack. All right, so it's a good first part. I guess we need to do a couple of things here. We have to put something S there because unfortunately for the energy, we're going to find that we need both the rotations. We need the rotation around this y-axis as well, because that contains some energy and we can't just ignore it. We can't just pretend it's not there. It's much nicer if we can, but we can't. So we know what the W is. We don't know what the IS is. We know what L is. We don't know what U is. We know what M is. And we know what V is. So we either have to find the moment of inertia or we have to find the speed. We'll just go ahead and get the speed. And that is the linear kinetic energy beforehand. So we've got two of these dumbbells again, and they both have the same kinetic energy because they both have the same masses and they both have the same speeds. So that's 1/2 times 2m v squared. And we still know all that information over here. And we have an exactly identical term except in U. Another kinetic, oh, I forgot the moment of inertia part. So we have the rotational inertia part times, I'm going to call it nu squared. And now that all is equal to, we have contributions from the dumbbells going backwards exactly the same except with U and another sort of thing there. So we have 1/2 m, well, it's 2m U squared, have to keep that in mind, plus 2 contributions of I, R, and we'll call it upsilon, which is a Greek U, and plus one last term for the kinetic energy associated with the spinning. So this is the kinetic energy associated with the rolling. Afterwards, we need kinetic energy associated with the spinning. We've got 2 dumbbells. We have a 1/2 times IS omega squared, like I intimated above. So let's see. We found this guy already. So he gets a check mark. This guy, we still don't know IS. We don't know what upsilon is. We don't know what IR is. We don't know what nu is. We don't know what IR is still. The same IR, we don't know it twice. We were looking for this U. That's what we wanted. We know what M is. So we've got all that stuff. And that is really ugly. It's prettier when I print it out, but it's still ugly when I actually type it. So you'll see a nice one soon. Hopefully it's the same equation. Let's see, 3. Let's hit. Let's hit the angular speed nu. We'll hit this guy here. So we got him. We'll need to get one of these. I want to get this nu. So we find that with the angular speed. And that would be, again, just the old thing. If it's rolling, then the rotational speed is just the linear, the ratio of the linear speed to the rotational speed is the radius of the dumbbell, like if it was a wheel. Which it looks a little bit like a wheel, right? So we can believe that. Nu is what we wanted, V we have, R we have, so that's not a problem. We don't get anything more out of that. We can cross that guy off. Cross this guy off. We didn't do IS, we did this other guy. Alright, so let's finish up the stuff in this term and find IR. We'll look it up with the moment of inertia. And that moment of inertia is, we've got 2 of them, right? We have 2 of these dumbbells, 2 of these weights on the dumbbell. Each one of those weights is sort of rolling circle And so rolling around that axis, if you look it up for a cylinder, is 1/2 mr squared. We know all that stuff. So we're good to go for that. So we've got the IR done. We got that IR. So next one up is upsilon. So we can find upsilon with, I want to do that because I have so little room, angular speed. So that's U is equal to, is it, no, it's not R. What is it? So upsilon, no, it is R. R upsilon. It's the next one that's different. Okay, so we were looking for upsilon and we had already found U. So nothing new in that one. And the last bit, the only question mark left is IS, which is the moment of inertia. In this case, the moment of inertia is, again, going to be twice something, because it's we're going to add up the moment of inertia from that plus the moment of inertia from that. The moment of inertia of that disk, and you can either look this up or you can find it from the perpendicular axis theorem, is 1/4 mr squared. And this is actually the reason why I said that these are very thin dumbbells, is because there's also another term to this that has to do with the thickness of the dumbbells. So if they're thin enough, we just can ignore it. So that's just what I wanted to do. But this isn't at the center of rotation, right? The center of rotation is the center of mass. It's right. If the dumbbell is rotating, oops, right, rotating. It's rotating around this spot right here, right? So it's rotating around here as it spins. So we have to move from here to here. So that means that we use the displacement, and the displacement is L/2 squared. So that's our displacement term in that. So that gives us all of those things. So it doesn't look as nasty as it looked the first time I wrote it all out, but it still looks pretty complicated. Okay, so that's sort of where we are. It's not really complicated because all we're doing is keeping track of two things. It's just that there are lots of terms, and now what do we have to do? Well, we have to get these things into some sort of form where we can compare conservation of momentum, conservation of energy, and get rid of this U. We want to get rid of this U, but before we can get rid of the U, we actually have to substitute all of these things in to each of those equations. Doesn't that sound fun? Maybe, do I have an eraser in here? Okay. Maybe I'll just try to do it all along here. I'm not sure how big it's going to get. It might get pretty large. Okay, so let's see. I want this guy, so that's 2 times 2 divided by 2, so that's just 2 times MVL. So A will substitute all of these things, 3 through 6 into 1, and that will be 2 MVL is equal to minus 2 MUL plus, all right, what do we have? We have 2IS omega. Omega is just omega, that's what we're looking for. IS is 1/4 times 2 is 1/2, and that's a quarter as well, so it's 1/2. Is that right? see, 2 times 2, oh, it's 2 times 2, so we don't have the 1/2, okay. So it's mr squared plus L squared. Okay, and these are single m's, remember, because they're for just one of the weights, right? And having 2 of them is accounted for by the factor of 2. R squared plus L squared omega. Okay, so that gives us A. And then B. Oh, look at all those things. All right, so what are we going to do here? So we toss that 2 in, so that gives us 2mv squared plus 1. Oh, the 2 and the 1/2 cancel, so we just have IR, which is 2 times 1/2 mr squared, so that's mr squared, and nu is v over r squared. So that's just, oh, that's just 3. Okay, so 3mv squared. All right, so we take 3 through 6 and shove it into 2. We have 3mv squared is equal to the u factor is going to be the same because it's the same mathematics all the way through, 3mu squared. And we have 1/2 is omega squared times 2. So that 1/2 is gives us an extra 1/2. So we have plus 1/2 m r squared plus L squared omega squared. Okay, so let's see. Yeah, I think that's right. How close am I? Looks pretty close to right. So now I've actually used all of these things. The only thing I'm doing now is trying to manipulate these 2 things. So the problem is going to be that I have to eliminate the u. So I have everything on the left-hand side of this equation. I don't have, I want to find these omegas, but I want to eliminate the u's. So I need those 2 terms to be sort of equal. I think the way I'm going to have to do that is to square this guy. So I'm going to have to square A, and I'm going to have u the u's be equal here. So let's see, I'll multiply by 3. And this guy here, I need these guys equal, so I square this one. That means I'm going to need an L squared, I think, right? So it's square this guy is going to be 4L squared U squared. And I can make that work. It'll be a little bit of algebra, that's okay. This guy's 3U squared, that's 4L squared U squared, times 3A. I don't have a 4 and I don't have an L squared, so this guy I'm going to have to multiply by 4L squared times B. All right, and I need to manipulate this first to get the U's on the left-hand side. So, you know, I'd do something like 2LU is equal to L squared plus R squared omega minus 2LV, right? And do the same thing with B. B, it's not too much of an issue, but then this one we have to actually square it afterwards, which is why we worry about getting U on this side, because this guy's 4L squared U squared. That's okay, but then this side we have cross terms, right? We want to not have cross terms with U in it, because then we can't get rid of the U's. So we square this guy and we square that guy, the 4L squared V squared. And then we have to have the cross term, which will be minus. Got a 2 here, so that means we have a 2 times a 2, which is a 4. L squared plus R squared. Times L, I think. That's what I'm feeling. Okay, so... oh no, I forgot the omega V. Okay. Alright, so that's reasonably good. We're alright with that one. Let's see what we can do on this other side. So on this guy, we just have to multiply by 4L squared. So I pulled the 3U onto one side and subtract the omega stuff on the other. So I have, or I have to multiply, actually I forgot to multiply this by 3. So we have 12 L squared U squared is equal to 3 L squared plus R squared omega squared plus 12 L squared V squared minus 12 L squared plus R squared times L omega V. So we have to do the 4L squared on this one now, so we have 12 L squared U squared is equal to 12 L squared V squared, and this guy is minus, because this guy has to go over on this side. 4 times 2 is 2, so minus 2 L squared plus R squared L squared omega squared. First thing is we can cancel the L squared U squareds here, as well as the 12 L squared V squareds. Alright, so that means we're stuck with 3 terms only, and 2 of those are an omega squared. So that will combine those. Oh, this guy's squared. So what is that? We have common factor of L squared plus R squared. We have 3 times L squared plus 3 times R squared, and here we have just 2 times L squared. So these guys add up because this one's negative, but it's on the other side. So that's 5 L squared, I think, plus 3R squared omega squared is equal to this guy, 12 times L squared plus R squared times L times omega V. Okay, what can we cancel? We can cancel the L squared plus R squared. We can cancel one of those omegas, which means we have omega on this side. We can divide through by the 5L squared plus 3R squared. 5L squared plus 3R squared. We have 12L, let's see. Okay, and so we have an L on this side here times 12, and then we have to multiply by V. So that is our answer. That's a little bit of algebra. That was fun. And each time you do it, it gets better, trust me. So let's see, what do we have here for our symbols? We have L, which we know, that's L there. We have R, which is here, so it's also given. We have V, which is also given, so that's good. We don't have any universals, so seems reasonable so far. Dimensions. Okay, what do we want? We want dimensions of frequency, which are t to the minus 1. What do we have? We have L over R squared times V. So that's the dimensions of L times the dimensions of R to the minus 2 times the dimensions of V. So that's length to the minus 2 times length times time to the minus 1, which just gives us inverse time. And that's good. So basically we've got a reasonable answer. At least we didn't make any obvious mistakes. There could be something else in there, but you know, that's all right. Let's see, what does this say? This says that the larger the dumbbells, the bigger the radius of the dumbbells, the slower the rotation. I guess that does make a little bit of sense. That makes sense because it increases the moment of inertia. I don't think that's something that is super obvious, especially since you have this decrease in the length as well, right? So right, that still increases the moment of inertia, but just not as much. And obviously we have the V. The V makes a lot of sense, right? The faster you're initially going, the faster it's going to rotate after the collision. All right, so that's it. Again, this is a conservation system. This is a collision. So we have these three conditions. And technically, all three of them were active, right? Because there are no external forces on the system. There's nothing like a peg or something that's going to keep us from using conservation of momentum. The only use for conservation of momentum, though, is to say that U and U are the same U. So if U are U, then U is good. So we didn't really have to use it. Maybe I could have used it and not assumed the symmetry part. Although, let me think. Is that really what the... I don't think that's really what the translational symmetry that comes from conservation of momentum means, but maybe I'm wrong. Conservation of angular momentum and conservation of energy, though, were both important. But we also had one of these axes where the momentum, the angular momentum, excuse me, canceled. So these guys were both good, and we used them to good effect. But, I mean, it's still ended up with a lot of algebra, which is why this is better in a video than in class. I really love this particular example. It's just that it's not something I can do in class, which makes the video so much sweeter. All right, well, it's nice talking to you. I hope you had a reasonably good time playing with this. And I will talk to you in the future. Bye now.